All right, good morning. Welcome to Wednesday of week 1. So according to the latest numbers, there are 293 of you and not enough of us. So we've added 2 faces to the board here, 2 new teaching fellows, and we'll continue recruiting a few others so that we will hit the ground running next week with the first assigned sections. That's your reminder as well to section yourselves at www.section.fas.harvard.edu. No later than 7 p.m. this Friday. The first week of sections were open. These next weeks will be assigned. So you will find out by email by noon on Sunday which section you're in and realize that sections themselves will begin Sunday onward. If you have any questions, talk to us offline. Finally, the first super section, so to speak, is today, Science Center B, which will feel huge compared to this room. And fewer of you will certainly go, but it's from 3 to 4:30 p.m. Again, this is meant to be an extra help session, a walkthrough, Q&A, and such. And as the term progresses, I think you'll find that these become increasingly useful as the material itself becomes more engaging and more challenging. So as for the room, we will see what we can do, needless to say, to install a few more seats in here or move us all together elsewhere. We'll let you know if and when that happens. So, flipping bits. So, turns out that flipping bits was perhaps not as clear as it might have been. So I spent all day yesterday thinking about how we can make this clear. And I came up with this example. So you wouldn't have thought that it would have been that complicated to pick a small example like the number 3. But it turns out that the number 3 in binary, as many of you noticed through your own and my own confusion, is sort of a perfectly symmetric. What we mean, though, by flipping bits, and get ready for a very animated demonstration, is that you go like this to flip bits, all right? So may this lesson always stay with you. That's flipping bits. It was purely unfortunate coincidence that flipping bits on Monday happened to be equivalent to doing this. But as you might imagine, doing this to change a number around is really not what's going on inside of a computer. So flipping bits does not amount to moving things around. OK, any questions on flipping bits? No? Well, then let's forge ahead. So you may have noticed that the course website's Bulletin Board is now active. So if you go to the course website, click Bulletin Board, what you will find there is a resource for you to use throughout the semester. You'll have to log in with your ID number and PIN. Ignore the fact that I'm actually logging in with my email address here. What you'll get once you visit the Bulletin Board is these 5 forums currently. So we certainly have this email address, CS50@FAS, which you're welcome to contact us at. But there's great benefits to be derived by sharing your own questions with others in the class. It certainly helps us so that we can answer one popular question once, and all of you can benefit from the answer, hopefully. Moreover, just to help you get over that hurdle that might be a disinclination to admit you're the only one in the class that doesn't know the answer to some question, all of your posts are anonymized. So even though you're logging in so that it's just CS50 students partaking in this, when you post a question, it will be listed as by a student. But however, when an answer or question or announcement is posted by us, myself, or the teaching fellows, you'll actually see our names. If you do ever see your name or a friend's name on the bulletin board, it means the bulletin board has what we call a bug. Since I spent all day yesterday changing the code that implements this bulletin board and ripping out all of the functionality that actually displays participants' names. As an aside, and this is actually a nice segue to a quick chat about the final project, the teaching fellows and I wanted to install bulletin board software this year. And in the past, the course has used similar technologies. It's always been a little slow. And so we essentially wanted the same idea, but a different product. So we Googled around, we asked around. And it turns out that the folks at MIT who implemented Scratch, if you noticed on their website, they have a forums link. And there's bulletin boards on Scratch's own website. Well, we liked their interface. So I emailed the guy, Andres, who implemented the bulletin board into their own website. We downloaded this freely available software. It's written in PHP. It supports a database called MySQL, which is something we'll introduce later in the term. We installed it into CS50's account. And then I began the process yesterday afternoon of looking through several dozen source code files, that is .php files, and ripping out all of this stuff that was specific to the display of people's names. And obviously, because we wanted to implement the display of TF's names, but not students' names, there are those basics laced throughout there. If, else. So all these basics are all you end up using to even do tasks like that. But any problems with the bulletin board are on me, since I was up rather late last night ensuring your anonymity. So I was also up late posting all the possible final project ideas that came to me within the span of 10 minutes. So I invite you over the course of this semester again to spend the next 2 or 3 months keeping your eyes out for interesting problems that might be solved on campus. As we've said, the final project is entirely up to you to design, though you will run it by our approval. But we do urge you, we challenge you to keep an eye out for interesting problems on campus related to campus-related issues, student group-related issues, or anything beyond that. Identify it and think to yourself, can I do better? Can I solve this problem by way of software? So among the ideas I tossed up here, and I'll leave it to you to flip through them if you find them of interest, Board Plus. So this is a random thing. My sister, when she was a grad student here, was living in the grad student housing, and they were required to subsidize essentially the dining hall that was within her building. And so they had to pay like $500 of Board Plus a year, and inevitably she had like $400 of Board Plus left at the end of the year. And even you guys, I think, get $50 every 65, so it's gone up since my day. So $65 a semester, and I'm guessing there are some of you who inevitably have leftover Board Plus at the end of the semester, and some of you probably out of it already. So this is only to say perhaps there's an interesting opportunity there, right? You have sort of a marketplace there, buyers and sellers. The only one that benefits if you don't spend that money is dining services, so why not see if you can put some of that money back in your own pockets? Can you somehow implement a marketplace by way of software, come terms end, solve that kind of problem? Shuttle Boy is this program that I wrote as an undergrad years ago. Well, I don't know much about Mac OS, so I've never actually implemented what's called a widget in Mac OS. Do it if you like the idea of looking up shuttle times on your own Macintosh computer without having to pull up a web page or such. It is a nightmare on this campus to actually reserve rooms. You have to know the person who manages the room or the set of rooms that you want to book a room in. And so you email or call that person. And when they don't reply, you walk over to their office. I mean, that is inviting a software-based solution. Harvard does not yet have that kind of integrated process. Those of you who have been or will be sectioning this week, it's not so bad to use from a student's perspective. But if any of you have ever head TF'd a course and have tried configuring, as these guys have, the online sectioning tool of FASs, it's a train wreck. Like, it is the most confusing thing to use. And even I have struggled with this in years past to figure it out. And that should not be the case. This is an example of poorly written software, but for a problem that's very compelling. Automate the sectioning process. Can you do better? So those are the spirits behind a lot of the ideas on the bulletin board. I invite all of you guys to post ideas, especially if you think those ideas are beyond your own means. Better yet, let someone else take that idea and run with it if you don't think it's something you yourself could do. But again, 3-4 months from now, I think many of you will be surprised just how much you learn in this course and just how much you're capable of yourselves in just a few months. Yep. OK. Let's say you come up with a genius idea. Can you sell it to Harvard? Can you? Sure. Will you? That depends on how persuasive you are. But by all means, if you can make money off of these projects, go for it. Right? An A and some dollars in your pocket. So this too, and I'm going to try to walk the fine line between being that self-promoting former undergrad who wrote this and actually turning it into an instructive example. But long story short, and I promise you there's motivation behind this. So Shuttle Boy was essentially this Unix-based program that I wrote after taking CS50 and I think 51 when I was a sophomore. The context there was that there were printed schedules at the time, but there was no shuttle time. There was no electronic means for looking up shuttle schedules. So that, too, was sort of this perfect opportunity for anyone to come in and implement a software-based solution. Facebook, again, is sort of the canonical example of that these days. There wasn't a Facebook. Now there really is. Well, at the time, I chose the far less lucrative path of helping Harvard students find shuttles. Clearly, I should have gone with the Facebook back then. But here we have what was essentially years later the port to the web. So I sort of resisted for years, making it web-based for various reasons. Now it exists on the web. And most of your friends at this school may not ever SSH to NICE or FAS at all. You all have sort of grown up on webmail and the like. But for the Unix folks, there's a program that looks like this. And essentially the way this program used to and still works, if you want to catch some shuttle, say you're at the Quad, and you want to hop off at Mass Ave, You click that, and then the website or the Unix-based program tells you the next few shuttles. So again, don't be amazed, if you even are, by this, but just let it be representative of the types of things we're talking about this semester, looking for opportunities and then going about and solving them. So there's this other segue, and this is meant to be, this demo is either going to be the thing you talk about after class or the worst disaster we've had yet. So for a year, you've been able to text the first 3 letters of 2 stops to txt@shuttleboy.com. So you can, using your phone via SMS, send an email or an SMS to that address, and then he'll reply with, say, the next few shuttles from the quad to the yard. So catch is that some of you probably don't even know how to SMS, that is text message and email address. And I recently got a new phone, and even I don't know how to do that anymore. I can SMS numbers, but I can't SMS email addresses. So this was sort of this opportunity, and I was like, all right, how can we fix this? Well, I'm familiar with things like Google. You can text message the numeric equivalent of GOOGL on your phone, if you've ever done this, and pose queries to Google. And that's sort of an interesting approach. So I wanted to get a phone number to port Shuttle Boy truly to mobile phones. So I asked around and such, and essentially I found a free service online that lets you sign up essentially for an account. And now, and this is where the demo comes in, and we'll see if their server can handle 293 text messages at once. If you would like to use a text message, feel free to opt out if you pay per message. But if you text message 41411, then you can't just text the number. You have to then give it the keyword, which is my program's keyword, which I chose it as short as possible. S-boy, capitalization shouldn't matter. And then you say something like Mather quad. So if I didn't screw up this version of the software, and I go ahead and pull up 41411 on my phone, SMS it, SBOY, space Mather, space quad, again choosing 2 reasonable destinations. I send it. Let's have a moment where we wait here. And OK, SMS has come back. And Shuttle Boy says it's 10:21, and you can go from Mather to quad in 2 hours at 12:20, 8 hours at 6:20, and 8.7 hours at 7 o'clock. So apparently not many people make the trek from all the way from Mather to the quad, though of course there could be a bug in the program, but I think it's correct. That's right? Oh, you have to connect? Oh, what a strange system. Anyhow, feel free to try this. In any case, again, it's not meant to be self-promoting. I did not sell this to Harvard, to be clear here. So this was really just a fun project that's sort of lived on far longer than I ever intended. So with that said, let's turn our attention to the matters at hand. The one thing we didn't demonstrate on Monday was this protocol, this type of program called SFTP, Secure File Transfer Protocol. This is a program you'll also use occasionally throughout the semester, if you've never used it before, to upload files from your local computer or lab computer to your FAS account, your so-called home directory. It's just an uploading/downloading program. So when you log into this program, and I'll do this from step 1 so that you've seen it once, and then thereafter are on your own, but know that there are handouts online that explain this. When you connect, actually, you'll see a prompt most likely on your computer or campus computer that looks like this. It doesn't matter if you connect to nice.fast or just FAS for SFTP. They all go to the same place when it comes to files. You do, when SSHing, to type commands at the prompt, need to go for this course to nice.fast. So that's the only distinction to make. We don't bother configuring SFTP for nice because it's just unnecessary steps. So I'm going to SFTP to FAS with our test account, CS50 test. I'm going to type in our password. And what you're going to see here is a window that shows you more of a graphical representation of your home directory. I've got a mail directory for email and my CS50 directory. I'm going to double-click that, double-click PS0. There's my questions.txt, in which I've clearly been writing up my homework answers. Suppose I've got my Scratch project here, oscartime.sb. Uploading the file just means click it, drag it, drop it. If you get a message like this, which some of you have asked about, SFTP programs can transfer files in one of 2 ways: ASCII or text mode, or binary mode. Essentially, the rule of thumb is that if it's a text file, it's in ASCII mode. And if it's anything else, it's binary mode. So let that be your rule of thumb. So if you're writing questions.txt, obviously text. If you're writing hello.c, What is that? Text. So it's just text, right? Hello.c was the name of the file I wrote on Monday to just write text that implemented a program. If you compiled the program and then uploaded a.out, that's binary. But source code is text. Question? Good question. Always trying to find the corner cases in lecture. So what if you drag two files, one of which is text, one of which is binary? This program should prompt you for each of them. Yep, and you can tell it to remember your answers for the future. So once I can, for instance, get rid of this and say, always use this transfer type for this file extension, and I'll never be asked again for Scratch files. If you have already, let me see if I can ward off a question that might come. If you've already submitted your work, but for whatever reason you uploaded your Scratch project in ASCII, most likely it will not work when we go to grade it. Just go ahead and resubmit before Friday. You'll simply clobber your original submission, but you're not late, so there's nothing lost there. Yeah, question in the back? Yep. Good question. Would a .doc, a Microsoft Word document, be binary or ASCII? It would be binary. So there too, the rule of thumb is if it is the simplest possible type of document that's just text, there's no even capability for bold facing or any of that stuff, it's just text. Otherwise, it's binary. Okay? Can't really go wrong uploading in binary, but you can go really wrong uploading binary stuff in ASCII. It has to do with new line characters and carriage returns being stripped off of the file. Yeah? OK, so what if you're using HTML? That's text, text, text. OK. For an exhaustive list of file formats, let's do some additional QA afterwards. All right, but use the bulletin board if you do have these kinds of questions. So let's go to where we left off the other day, which was here. How to write a program in C. So again, these rules are universal whether you're doing the principles are universal whether you're writing programs on a Unix machine, Mac machine, Linux machine, or any other. Some of the specific commands we show you there, though, certainly are specific to, say, Linux environments or CS50's Linux environments. So the very first program we wrote in C on Monday, and the only program we wrote, was hello.c, or I think I called it hello1.c. Here's nano. The first thing I typed, recall, was include standard IO. Then I said something like int main, int argc, char star, argv, PrintF, hello world. And then once I fixed that initial bug, we then had, hopefully, a working program. Control X saves. GCC is the name of the compiler that we'll use to compile this. It suffices just to type it like that. You get nothing in response, but if you do an ls, you'll see a.out. And if I run a.out, I should now see my program in action. Yes, question? Sure, let's see. How's that? OK. So that's it. So that's the simplest of possible programs, perhaps, in C. Where can we actually go from this? And what's actually interesting to note? So this thing here. So the very first thing that gets executed, so to speak, that is run when you run a program that was written in C, is this so-called main function. So henceforth, anytime you see something that looks similar in structure to this, like a keyword like int, followed by a name like main, followed by parentheses with some stuff in the middle, that's most likely what's called a function. And a function is essentially like a miniature program that your program could call. By default, when you run a program that was written in C, it is the so-called main method that gets executed. If, by contrast, I goofed and I said, just call this a function, and I didn't call it main, well, what's going to happen here, if I rerun GCC, is you get undefined reference to main. Well, what's that saying? Again, these messages throughout the term will, on first glance, seem cryptic. But what it's saying is main doesn't exist. Go put it there. So if we go back, we can then go ahead and fix that problem. All right, so what else is there that's worth pointing out here? Well, there's clearly this one-liner that constitutes this program ultimately. This thing we'd call PrintF. So this is another example of clearly a So a function, right? It's like a miniature program, apparently, that clearly has the effect of printing something to the screen. And the F in printf is for formatting. You can print formatted strings. And we'll see more about what that means. So why is this useful? Well, when you first pull up Nano and just have a blank file, you don't want to start coding in zeros and ones and telling the CPU exactly how to behave. Much nicer is it if you can leverage the work of others, work that other people have done, namely implementing the process of displaying characters to the screen. Well, back in the day, the folks who implemented precisely that functionality, the ability to print messages to the screen, they wrapped up the code they wrote, put it in a function called printf. They installed it on Unix systems throughout the world, including this one. And you now have access to that functionality by way of this function called printf. So this idea of functions, on first glance, certainly lets you reuse code. Not necessarily your own, but the code of others, so that you as programmers are not constantly reinventing the wheel. This is how software development over the years has progressed. People write very good implementations of basic functionality, like in this case, printing. More modernly, functionality like the ability to operate on the internet, that is, open network connections. And then we, sort of the more ordinary developers, can build upon the work of those other people and make yet more interesting software. And as the years progress, typically people implement what are called libraries. Those are just collections of functions and other things that then they make available for the world to use. So that first line of the file there, include standardio.h, stdio.h, is the name of a file that contains C source code that someone else wrote. And the mere fact that I'm typing include for that file at the top of the file means I now have access to all of the functionality that whoever made that file put in there. If I forget to include this and I try to save my file and then I run gcc on hello1.c, you'll get either sometimes an error if you do a mistake like that, or at least a warning. Here we have warning, implicit declaration of built-in function printf. So even if you're not quite sure what that means, it clearly means something's awry. And in this case, it just means that we forgot to tell the compiler, GCC, exactly where to find all of the functions that I'm making use of in this program. OK, so programming 101 in C. Questions? Yeah?
So that means include this library?
Include this library, exactly. So again, a library is a bunch of code that someone else typically wrote that you are using so that you don't have to reinvent whatever wheels they already implemented. Now notice, it's not just a matter of calling, so to speak, or invoking. These are all synonyms for our purposes, printf, but we seem to be passing it something. Inside those parentheses, generally, are what we call arguments or parameters, depending on the context of the conversation. Doesn't really matter. Inside the parentheses are things you can pass that affect the behavior of that so-called function. So it wouldn't be a very interesting program if all we did was call print, but didn't tell the function what to print. So we can control its behavior by way of this argument. And it looks like printf takes at least one argument. And this is what we'll call in the future a method, a function declaration, a signature. The nomenclature is not so important just yet, but what it means is that printf takes at least one argument. You need to tell it what to print. Well, fortunately, we can do more interesting things than hard coding in strings like that, and we'll see in just a moment. But there was that weirdness in there. Remember on Monday when I first ran this program, it looked a little sloppy. And you know, it's debatable as to whether it was wrong or not, but there was no new line character. And a new line character is the act of hitting enter or return on your computer. Well, C supports these things called escape sequences, so that you have a way of expressing keys on your keyboard that don't really have symbols that you would normally look at, because hitting enter just moves the cursor. It doesn't really display anything usually. \n means new line. \r means carriage return. \t means a tab character. You can guess what the second one is. Just it means a literal quote. Because if you ask yourself, how do you actually print a quote? If you've got a quote, the quote, well, so as not to confuse the computer, you escape it by putting a \/ in front of it. For example, we might put arbitrarily hello world in quotes. Now, the coloring is a little strange because Nano's trying to give us a hint there. Let me try and compile this as is. And this is where the messages just get unhelpful because it doesn't quite know how to express the problem. But what it means is now the compiler doesn't know where things begin and where things end, but we can fix that by just actually quoting, or escaping rather, the quotes that we want to run. Now it did compile, and now it says hello world. Okay, so simple stuff, but representative of where things to come. This last one, what does that represent? Backslash, right? So if backslash has this special meaning, how do you print the backslash? It's sort of like a recursive problem. Well, you just escape itself just once, and it will work. A quick note on this carriage return. So what's the difference between a new line character and a carriage return? OK, so how many of you have ever used a typewriter before? OK, so not bad, a few. So a typewriter, and actually I don't even remember how typewriters work, but I think on some typewriters you could hit a button, or maybe even the old ones where you had to pull a crank. So originally, and I'm going to make this up as I go because I don't remember. So originally, the way typewriters used to work is you would like pull a lever or push a button, and the paper wouldn't scroll up a line necessarily, but the little thing that hits the ink on the paper would just return to the start of the line. That's a carriage return. A new line actually scrolls things up by one line. So C allows you to express this distinction. You can literally move the cursor to the next line, and by default, it will end up all the way on the left. So it's sort of both in a sense. Carriage return leaves the cursor essentially on the same line, blinking, but moves it all the way to the left. And that actually is not just a random trivia to point out. That actually has some utility, which we'll see. All right, so that's all fine and good. We now have the ability to write hello world, but we had that ability last week. And all it took last week was the dragging of a puzzle piece. What more can we do with this environment? Well, fortunately, programs can take input and produce output based on that input. The output itself certainly doesn't have to be hard-coded into the program as we've done here. The means, as you might guess, via which you can control the behavior of a program dynamically is by way of variables, which by definition vary in their values. And better yet, you can ask users to provide input for those variables, which was actually something that you could not do with Scratch. So what might we do here in, say, an example called math1.c that we couldn't do before? So nano of math1.c include standard io.h int main, and it's quickly I will stop recreating all of these from scratch once it becomes sufficiently clear what we're doing, and just work off of the canned example. So here we have our template for the next function, and I just want to do something with math here. So what might we actually do? Well, turns out that C supports math. If we want to do something like PrintF and say something like the sum of 2 and 3 is, and I want to put in the answer here. Well, obviously, the easy solution is to say that. But let's make our lives harder for no real reason just yet. I'm going to leave it blank, comma, and now I'm going to do the math here itself, right? I'm clearly not good. Clearly not good with math. So I'm going to let the computer do it for me. So I need to tell the computer, or specifically PrintF, to get ready for a value there. I need to give it a placeholder. Because recall that PrintF did take at least one argument, but then there was this ... Well, what that represents is the potential for PrintF to take multiple arguments, namely variables and values that need to get substituted in to the format string, the thing between quotes. If you want to output a number, the placeholder is %d, essentially for decimal value. All right, I'm going to put in that \n now so that things look pretty. I'm going to go ahead and save it. And those of you who like keyboard shortcuts, what I've been doing to save time is if you hit Control-Z, it suspends the program rather than quitting it. And then FG is foreground in a Unix environment, which brings it back to the foreground. So GCC of math1.c, enter. It seemed to compile OK. I'm going to run a.out. All right, so I have my first working program. Completely underwhelming, though. So can we actually use variable inputs and variable outputs? Well, again, we do have this ability in C to express variables. And we've talked about bits and representing values verbally and with our demonstrations and with our bite of humans here. But how do you do it in real terms? Well, C provides you with 4 different types, data types, of variables. You need to tell the computer what type of data you want to store. Scratch only had number variables, so think of C as having number variables and some others, more refined. You can have a character, aka char. Some people say care. I never understood why people say care. Char is how I would say it. It stands for one character. So as soon as we start getting into character strings, our crypto problem set, we're going to be focusing on chars, characters. They only use, and this kind of stuff will become old hat soon, a char only uses 8 bits, which means the total possible number of characters that you can represent with a char in C is, of course, 256 total. That's a problem, actually, for languages other than, say, English and other Romance languages. Asian languages often have more, for instance, than just 26 characters or even 256 characters. What you need, then, is more bits for those kinds of languages. So even though C, back in the day, was really tailored initially just for 8-bit ASCII, 256 possible characters, know for now that there are newer, more appropriate systems. Unicode is the buzzword there, that do use, say, 16-bit values or a combination of 8 and 16-bit values to express other languages' symbols. For now, we're just going to be dealing with char. An int, fast forwarding there, is a variable type that stores, obviously, an integer. An int takes up 32 bits on most systems, certainly on nice. In between that, we have on the board there doubles and floats. So take a guess. What is a double? Or what is a float? So it's a floating point value. So an integer is just something like -1, 0, 1, 2, 3. A floating point value is essentially a real number. It can, by coincidence, be 1, but really it's like 1.0. And if you wanted to express, say, 3.14, etc., well, you would use a floating point value for that. And in that case here, a float is, I believe, on a Unix system, 32 bits. All right, and take a guess what a double is. Really big. OK, not quite really big, but it's twice something. So it should be on most systems 64 bits. And what that means is that you can either store in what's called a double either bigger values because you have more bits to play with, or you can use more precision. That is, if you want to approximate pi to a ridiculous number of decimal points, well, you can use a double to be more precise than you could with a float. Just know that these values can vary on system to system, but for our purposes, they will pretty much remain fixed throughout the term. All right, so what can we actually... Oh, and as an aside, the little footnote here. In C, you actually can specify more carefully what kind of char, double, float, and int that you want. We talked briefly on Monday about negative numbers versus positive numbers. Well, if you just use an integer in C, and therefore by default it can be negative or positive, how many different values can you represent roughly using 32 bits for an int? It was like 4 billion. But if you want to represent both negative something or other and positive something or other, there is a cost there. What's the biggest positive value you can represent, presumably, then, with 32 bits? It's like 2 billion. So that's the trade-off. But if you want to specify to C, to the compiler, I really want to deal with big numbers, or I just don't care about negative numbers, let's not even run the risk of making mistakes and tolerating them in the program, you can tell the compiler that this is not only an int, but it's an unsigned int. And you literally write unsigned space int, and then your data type is not only an int, but it's guaranteed to be as big as 4 billion if you want to put that value in. Long and short allow you to express longer versions of some of these values. They get prefixed typically to int. And one of the stupidest things you'll see, for those of you, especially with some of the hacker editions of problem sets, if you want to deal with really large values, it turns out a long, which is just a int, is how big on a typical Linux system, would you say? Yeah, you'd think so. 64 bits. It's not. It's 32 bits on, again, most systems. But if you need 64 bits, you can use a long and that's 64 bits. So a lot of this is for historical and legacy reasons. So just FYI, for now that's not so relevant, but for those hacker editions you might need to have that kind of control. So a quick summary so you've seen them of these format strings. I use that %d as a placeholder. Turns out you can use placeholders for other things. So %c stands for character. If you want to dynamically plug in some character that's in a char variable. D is an integer. E and capital E are for scientific notation. For numbers, we tend not to use those so much, but know that they exist. %f is for any floating point value. So that works for doubles and floats, it turns out. And incidentally, know that there are good online references here if you don't want to scribble everything down. %u is, what is that, unsigned? So an unsigned int. And %x is for hexadecimal. The most important ones probably for now are C, F, D, and S, which is string. So if you have a string that you want to express. So let's actually see these in action. So what can we do that's slightly more interesting now mathematically? Well, let me go back to my example here. I'm going to make a copy of math 1. I'm going to call it math 2. And incidentally, I think it's incredibly frustrating as an audience member if you have to be scribbling down code as I type it. So know that what you essentially have in today's handout is a sort of the can demonstrations, which I might stray from sometimes based on questions, but know that this is sort of your reference for what we ideally did in class. So you don't have to write down source code. The idea of my typing this stuff dynamically sometimes isn't, again, to bore you, but really to see if we can engage at least some of you to sort of try to think a step ahead of me as we implement this so that you can see or guess for yourselves where we're going. So I use the cp command to copy a file like that. And now I've got a copy called math2. And I just want to do something that's actually credible here. I want to declare a variable called x. And let's assign it the value 2. Hit enter. I'm going to declare a variable called y. And I'm going to assign it the value 3. Now I'm actually going to do something a little more intelligent. I'm going to say a variable of type int called z is going to get the sum of x plus y semicolon. Notice there's a theme here. Almost always when I end a statement in C, it ends with a semicolon. That's essentially the rule of thumb. All right, down here, I can make a change. What do I want to actually put here now? Yeah, so just put Z. I'm going to save it with Control-O. I'm going to go back to the command line. Another keyboard shortcut I've been typing is instead of typing GCC, say math2.c multiple times, on a Linux system you can hit exclamation point, aka bang, and hit G, or the first one or more letters of the command you want, and the computer will figure out which of the most recently commands matches what you just typed. And that, too, will save you time in the aggregate. We've compiled it. I'm going to run a.out. And again, the sum is still 5. So a baby step, if you will, toward using these variables, but it will quickly become more involved. Let's take a look at, say, size of, just to introduce another operator. So I'm going to go ahead and in our hidden can demos here, open up this thing, sizeof.c. And you're going to see a couple of things. You do have a printout of this. It's wrapping a little ugly because I've blown up the font to fit it on the screen. But in general, these things print nicely and display nicely on a normal screen. All this stuff up top. It's clearly not programming code, but it's what's known as a comment. The way you write comments in C, which are really reminders to yourself, instructions to a teaching fellow, explanations of how your code works, is quite simply a / star, write whatever you want, and the comment ends as soon as you do the opposite, */. And it can span multiple lines. There's this convention, and it looks a little ugly here. If you look at your printout, you'll see the true effect. People just for sort of pretty aesthetics tend to flank, say, the left side of their comments at the top of a file with all these stars. It's completely unnecessary, but it's just convention. Do really as you see fit. And in section, will we teach you these concepts generally known as style and how to write not only correct code, but readable code, elegant code, and well-styled code. So scrolling down is where the real stuff begins. Notice that whether or not you have white space in the file here and there doesn't really matter. That's for humans' purpose. Notice here now that I've declared a few local variables, not just x, y, and z as ints, but this is how you would declare variables of other types. The type, the name you want to give the thing, followed by a semicolon, or you can actually assign it a value with equals, as we did. Down here, we use PrintF 4 times. It looks the same almost for all of them, but size of. I mean, take a guess how this C operator is going to do for us. Well, it's going to print the size of something. What do we think we'll get if I run a.out now? What's the first thing that's going to print? Char colon what? OK, 8. How about double colon 64? All right, so let's take a look. I'm going to run a.out. Wrong. OK, why? OK, it's just doing it in bytes. OK, no magic there. Just everything's divided by 8. Size of tells you the size of these values, which is useful for today just to confirm what we did sort of off the cuff here on the board. But this actually does have utility in programs when you need to check the value, not just of a primitive, as all of these basic data types are called, but of structures, for instance. We're going to see before long that using C, you can also create your own structures, your own types of variables, a student structure, maybe a course structure, maybe a shuttle structure. Anything you want, you can sort of combine multiple pieces of data and roll it into one thing that you yourself give a name to. So that's the size of operator. All right, arithmetic operators. We're not going to do examples of plus, minus, multiplication, and division, but know that they all exist as such. This last one, though, is worthy of note. We've seen % before using those formatting strings, but here it has different meaning. When it's used as a binary operator, that is to say something like this. I'm going to go ahead and open up, let's see, copy math 2, and just call it temp.c for a moment. In temp.c, what I'm going to do is this. Let's say I want to output a number just for demonstration purposes. And now I want to go ahead and do, let's say, 10% 2. Semicolon, save it. I'm going to compile temp.c. I'm going to run it. 0. All right, now I'm going to make one change here. I'm going to change the 10 to an 11. And I'm going to recompile it using my keyboard shortcut. I'm going to run a.out again. Oh, and the other keyboard shortcut that's quite useful, when you start typing a command, you can actually get lazy, stop typing the command, and instead hit tab, and the computer will guess what you mean if there's a unique match. That too will save you time. OK, 1. So 10% 2 is 0, 11% 2 is 1. And that pattern is actually going to repeat because this % operator is actually the modulus operator, mod. So you have this ability in C to take the remainder of a value. So that is to say, what's the remainder when you divide 10 by 2? Well, it's 0. In other words, 10 mod 2 is 0. By contrast, 11 divided by 2 gives you a value with a remainder of 1. And so 11 mod 2 is 1. Now, that might seem silly, but of all the operators, that is perhaps one of the most useful. And it will come up in very useful contexts and offer interesting solutions to problems that you might not think obvious. A note on precedence. Much of this table will we fill in the meaning of over the days to come. However, know that in C, there is predetermined rules as to what's got to get evaluated first. So just like in grade school math, there's rules like multiplication's got to come before addition or subtraction. Well, same deal in C. Not only do they borrow all of those grade school ideas for arithmetic, also there are other operators in C that we'll begin to see. And just know that if you're ever writing a statement that's using a bunch of these crazy operators, it's important to know, or certainly it's helpful to know, which of them is going to get executed first. Because if the order is not what you expect, the odds are the program behavior is going to be wrong. So this is sort of a cheat sheet. There's another version of it at that URL. And there's yet another version of it in the recommended books. It's all over the place. You can also Google C operator precedence, and you'll get charts like these. But they tell you left to right, top to bottom, in which direction things associate and what has higher precedence than something else. Yep. What if you want to type 2 numbers? Excellent question. So let's, instead of this, say, how about this? %d equals %d. Now I can say 2, 3, 5. Again, there's no reason to make this program because it's rather simple. But if I now compile temp.c and run it, you do have all 3 numbers substituted. Is that your question? OK. And you can do that with other data types as well, which we will quickly see. All right, so what else can we do? Well, when printing things, you do have, again, within PrintF, these formatting strings. And these formatting strings actually allow you to exercise a bit of control over the amount of space that numbers take up and also the amount of precision that is shown for variables. I'm going to open up one of the files that you have in your printouts called math3. And in this file, above the comments, notice we have this. So I arbitrarily said, give me a variable called answer of type float, 17 divided by 13. All right, and actually, before we do this, I'm going to change something. I'm going to get rid of this, and that's it. Let's see, do I want to do that? All right, yes. So now I have math3. The only change I made temporarily is to remove what was a decimal point. So I'm going to go ahead and compile this thing, GCC of math3. I'm going to run a.out. And it appears that 17 divided by 13 is 1.0. Even though the answer is supposed to be a floating point value, and it is, but it's not 1.0. And I specified the right format string. In fact, notice the .2. Using this dot number notation, can you specify even more precision? If I change it to 10, recompile the program, rerun the program. OK, more and more precise, but more and more wrong. So what's going on? And again, it's sort of a leading question because I fixed or I broke what was correct a moment ago. So the answer is not add a decimal point. Why?
You have to make one of the numbers in 17 and 13. You have to make one of them a floating.
Yeah, exactly. So by default, values in C are ints. If you write an int, it's an int. The result is that 17 as an int divided by 13 as an int is 1 point something. But you can't store somethings. You can't store decimal values in ints. So what the compiler does is it throws it away. And it leaves it with just an int of value 1. And then it's that 1 that gets assigned on the left-hand side to the value answer. There's a couple ways to fix this. The easiest way is to just be explicit and say 17.0 divided by 13.0. Recompile. Re-execute, and now we've got the right answer to 10 decimal points of precision. I was trying to be sort of slick and crafty. I just put 1 decimal point, and usually that suffices. So long as one of the values in the expression is a floating point value, essentially everything becomes that type of value. So if I recompile this, rerun that, now I have the same value as well. And there's yet one other way to do this, and this will come back in the weeks to come as well. You can explicitly tell the compiler to cast one data type to another data type. Now, sometimes that makes sense. Other times, it makes no sense. You wouldn't want to cast a string to an int, because just intuitively, that doesn't make sense. And we'll see technically why. But if I manually specify with parentheses and then the name of the data type that that thing's a float, recompile it, rerun it, now that example works as well. All right, so these, again, I would refer you to this online reference for the nitty-gritty details as to how to control the appearance of your output. This will become useful when it comes time to write larger C-based programs that have printed output that you actually want to control the behavior of. And not to dwell on it, but Shuttle Boy, for instance, with its use of those columns for times and durations, it uses PrintF. And it uses the width field of PrintF to make sure that all of those times and durations takes up the same amount of space so that everything looks like it's formatted in columns, even though at the end of the day, it's purely text. Well, there are other data types that are useful to use. C does not come with them. In fact, Boolean variables or Booleans, the notion of a Boolean, true or false, C does not have by default. C also does not have conceptually the idea of a string. It does allow you to use strings, which are just sequences of characters, but it does it in a way that we will reveal the details of in a week or so. What we've provided you with for this semester is what's a CS50 library. So you saw the standard IO library briefly earlier. Well, we essentially have a CS50.h file as well that provides you guys with a bunch of functionality you'll find useful. In that file are things like a Boolean data type and a string data type that you can use. And we'll take a look then at this hello example. In hello2.c, do we actually have now a program that's marginally more interesting than our first, in that we don't hard code hello world, but we actually swap in the value of a variable, and that variable is of type string. It's not hard to imagine how to use this, but compiling it is worthy of note. We've added here to this line to include the CS50 library, because again, strings do not exist in C, but they do in the CS50 library. If I go ahead and compile hello2.c, it's going to execute as such. If I run a.out, you'll get hello David. We will see, though, in the future that there are several functions in the CS50 library that will allow you come Friday to get values from the user and then display or manipulate those values, for which we'll also compile in. We will see you on Friday.